I'm going to show us a little bit about how forces and motion work with an example of pushing a large object, such as this crate. This is a simulation that comes from the University of Colorado's Physics Education by Technology program, PHET. And the simulation of a large crate is something we can imagine how it would go because we're used to pushing heavy objects with all of our might. But we're going to, into this simulation, choose to take on the situation which is a little bit less familiar, one where there's really no friction involved. And we can imagine this large crate is not scraping along on the ground, but rather is on some nice smooth rollers. And so the friction is completely turned off. And I want to go through this so as to give a sense of how the force that I apply pushing this crate along translates into an acceleration and to position and speed, much as we would expect from Newton's laws. So let me just play through this simulation briefly here. So the crate's currently located over at minus 10 meters on this number scale, that's right there. And I'm going to push it. So here I am. I'm applying a force, and you can see this force arrow indicating right there what's happening to the speed. During the time I'm applying the force, the speed is changing. That's Newton's first law. And so I'm going to just pause that for a moment. Remember what Newton's first law says, that an object in motion tends to stay in motion, or an object at rest tends to stay at rest unless acted upon by a force. And so anytime I see a change in an object's motion, or in other words a change in speed, is when I expect to see a force. So let me continue the little video here. So I've pushed it, now it's up at some speed, and notice it's moving along at about 1.2 meters per second. In other words, if I'm not pushing it, which is the case because I'm standing over here way on the left, then it should be just moving at constant speed. Well, there I applied another big force, and I pushed really hard, so the change in speed was rather rapid. And now it's going to coast along again because I'm not applying a force. And now I'm going to give it a push from the other side. So here's a force arrow indicating to the left, and I let go. And I'm worried about hitting my house here, so I'm going to give it another big hard push, a really big applied force to slow it down. I didn't quite succeed. I better give it another push here as I go along. And I think I just managed to get it to stop before it hit my house at 10 meters. So every time I stop pushing on this thing, it's not that the object was required to stop, it's merely that it was required to stop changing in speed. That is Newton's first law. So we have to keep thinking about forces causing a change in speed. And if there's no force, then there's no change in speed. This is really counterintuitive to us because we're used to working in a world with friction, where whenever we push on something, it eventually slows down if we stop pushing. But if we imagine a world like a crate on ice, or a crate on perfect wheels, or we're pushing on a large heavy ship in outer space, when we give something a push and then we stop, it will keep on moving. So in all these regions of this graph, like right here, and right here, and here, and here, I had pushed on something but stopped. So there's no force being applied, and yet the object is still moving. It still has a speed of either 1.2 or 2.6, a little bit less than 2.6, maybe 2.2, or 1.0 meters per second. In all these cases, the speed was not zero, even if the acceleration was zero. Well, I've said the word acceleration. Maybe it's worth it if we just plotted the acceleration separately. This time, I'm going to graph not only the velocity of the object, but its acceleration. Let's play through the same simulation. Here I am, I'm giving a big push, I'm applying a force. Notice what's happening to the acceleration right now. It is not zero. So right here, the acceleration is above 0. That's the same place where the slope is positive on this position versus time graph. Now I've stopped pushing. The acceleration is 0, and the slope of the velocity graph is 0. Now I'm about to push again. The force that's applied is very big, and the acceleration is very big. It's bigger than the last time, and that's because of Newton's second law. Force is equal to ma. The bigger the force, the bigger the a, the acceleration. Notice I stop pushing and the speed is constant. Then I'm going to give a backward push. That means a negative acceleration in this direction. And then I'm still worried about hitting my house, so I'm going to give a big backwards push. That's a big negative acceleration. And the speed ramps down very fast. Notice the slope of that line right here is very large because the value of the acceleration is very large. Then I'm going to give another tug backwards. So in this region, I have an acceleration that's negative, and once again, I have a slope of that line that's negative. So there's several things that are important here. Remember that acceleration is a change in speed. In other words, it's a delta v over a delta t, or it's a slope. So if ever I see an acceleration that's large, then the slope of the speed versus time graph has to be large. If the acceleration is not large, then the slope of the speed versus time graph has to be not large. So that's Newton's second law coming into play. Now just to go back and connect with our kinematics, let's see this again, but this time not graph the acceleration, but instead let's graph the position. So I'm pushing hard on the crate right now. The slope of the velocity graph is going up. And notice that the position graph was changing quadratically right around here. Then I'm pushing again, and right in this area, the position versus time graph is changing again. And now here it's constant because the velocity is not changing. It's constant. But at the moment its velocity starts ramping down is when I see another shift in the position versus time graph. And here it's going to ramp down again because I'm pushing backwards. It's about the point where I start to see a change in the slope of the tangent lines to the position versus time graph. So the simulation does a good job of exemplifying the principles behind Newton's first and second law, namely when I'm pushing on an object, I'm applying a force, then I should see a change in speed. That's all these locations right here and here. Or here, or here. If I'm not pushing on an object, then it doesn't mean that the object can't be moving anymore. In fact, here it's still moving, and here it's still moving, and here it's still moving. It's just that it's doing so at constant speed. So it's okay to have an object in motion, it has to be constant motion. So Newton's first law says an object in motion stays in motion, or an object at rest stays at rest unless acted on by a force. So a change in that process, a change in that speed, is equal to a force. And the magnitude of the force tells us something about the magnitude of acceleration, because, as we wrote before, force is equal to mass times acceleration. So when this big is big, then this has to be big. And when acceleration is big, like in here, then the slope of the position versus time graph has to be pretty big as well. We've also seen cases where the acceleration can be negative as opposed to positive. So here it was positive. Here it was negative. And that corresponds to the slope of the speed graph being positive, or the slope of the speed graph being negative. Because acceleration is just changing speed.